Hey everyone, welcome back. So today we're going to be talking about an application for the block encoding methods that we've been talking about so far, and in particular, the quantum singular value transformation. The application that we're going to talk about today is going to be linear systems of equations. So let me get this started up. So the key problem of the quantum linear systems algorithm is the following. Let's say that what we want to do is we want to be able to solve the following system of equations. We want to be able to solve AX equals B. Now, we're going to assume that this is known, and I'll explain a little bit later what we mean by known, and also that this is known, but X is unknown. And we'd like to be able to find X. Well, A here we're going to assume is a matrix that in our context is going to be 2 to the n by 2 to the n dimensions. And furthermore, we're going to assume that it's invertible, and we're going to assume that A equals sum over J, alpha J, uj, under the exact same assumptions that we normally have been making, such as alpha sub J is greater than or equal to 0. Okay, and each of these uj's are unitary. Okay, wonderful. So in any case, once we've made this assumption and assume A is invertible, then the unique solution to the linear systems problem is that X is equal to A inverse B. Okay, where again, X is a vector of dimension 2 to the n here. Okay, fantastic. So then if we want to be able to solve this on a quantum computer, the entire problem basically boils down to the problem of mapping our solution onto a particular quantum state vector. So the way that we quantize this problem is let's let X go to ket X, B go to ket B, and assume that we have an oracle UB which maps 0 to the vector to ket B, which I'll define to be the vector B divided by the length of B. And the reason for this is because of the fact that in quantum, obviously, everything can only be unit vectors. Now, if we really want to be able to do this and keep track of the length of vectors, we can do that. But we just need to store the length in an additional subspace, which is kind of like a block encoding. So we can embed a non-unit vector as a subblock of a larger unit vector. But for the moment, let's ignore that in our problem. Okay, so now we have that. Our goal is to end up finding, so we want to find a vector x tilde, which is equal to all right, I guess what I want to say is we want to find a vector x tilde such that the norm, like the Euclidean distance, for example, of that vector x tilde minus A inverse B divided by the length of A inverse B, we would like to be able to find an approximate solution to this within error epsilon. Okay, and specifically, we want to be able to, the problem is to yield the quantum state, not to yield information about the quantum state. Obviously, once we have X, we can measure any expectation value of any term we feel like, just for example, by using the good old fashioned Hadamard test on this. Whoops, this would be chi tilde coming in here. And I should put a tilde up here. Okay, so this will allow us to be able to compute the expectation value of any unitary U if we feel like, and we can use this in order to be able to find moments of the resulting distribution in polynomial time. In contrast, if we take a look at finding the explicit solution, the cost of doing a inverse is in order 2 to the 3n. And so what that ends up meaning is that the cost in terms of the number of operations ends up going like, well, the cost of a inverse ends up going like 2 to the 3n. So the cost is exponential in n. All right, so that suggests that if we can provide an algorithm to solve the quantum version of this problem that satisfies 1, the total number of queries, 2, the prepare oracle, which again, we'll just map 0 to sum over j, alpha j divided by normalization constant alpha with square roots here, and select, which maps j psi to j use of j psi. Then these, the number of queries to that, and furthermore, what we're going to need is we're going to need a oracle we'll call prepa that it will end up block encoding the a over alpha inverses coefficients. I'll get to that in a sec. If the number of queries that we end up making to this are in poly n, and 2, if each can be reduced to gates in poly n, poly n gates, then it's possible that this algorithm is efficient. And so we'll go through and we'll argue that there will at least exist instances where this is conceivably efficient. Okay, so moral of the story is that we can get exponential speedups under some circumstances for this particular problem. Okay, so let's just go through how this all works. The first bit that's needed is we need to figure out a way to block encode A inverse. Okay, so specifically, how are we going to do this? Well, the basic idea, if you recall, was using prepare and select, we can construct a block matrix that's of the form A over alpha and a bunch of junk out here. Then using a quantum singular value transformation, which was a circuit that ended up taking a form prep and then from that we ended up having a series of controlled unitaries, controlled select gates. That ended up looking like the following. So we triggered off of every single one of these prepare registers with a coefficient coming in from the top. And here we've defined prep A acting on 0 goes to the sum over j, A sub j square root divided by normalization constant, square root A. And then let's call this P. And then P sub U over here, where this is a unary encoding. And specifically the type of unary encoding we ended up using, if you recall, was where we have like, this is the deck if we have the decimal representation over here and we have unary, the form that we end up using is that these two are the same. And then, whoops, 2, 1, 1, 3, 1, 1, 1, so on and so forth. And we do that just to end up making the control logic easy to express. Okay. And we found that if, let's let f of a over alpha equals sum over j, a sub j, a over alpha to the j equals 0 to k, and we put k qubits up here, then this circuit in particular, we found will create a block encoding of the form f of a over alpha inside an even larger space than the original one because of all the extra registers needed to store all the prep states, which hold the coefficients, the alpha coefficients for each of these matrices in here. Okay, so this is the way that we can block encode an arbitrary polynomial of a over alpha. Now, our task at this point is actually to end up going through and figuring out how to build an appropriate polynomial for the inverse function. And so there's a couple of different strategies that we can use to end up finding a polynomial. The first one is just to give you some intuition behind it. I'd like to spend a little bit talking about how we could build a Taylor series polynomial for this. Okay, so Taylor series, they work great when they work. But one of the big problems is that Taylor series actually tend to converge relatively slowly if we want to have a global approximation. So a Taylor series, basic idea is that, imagine we got some crazy function over here. A Taylor series gives you a local extrapolation of a function about a single point. So say we wanted to expand about this point. Well, the 0th order Taylor series expansion, which I'll draw using this, would be that. The 1st order Taylor series expansion, let's try to find something. Yeah, I kind of like that color. Okay, 1st order Taylor series expansion locally would end up looking like this. Then 2nd order might look something kind of more like following. And so you can see that what we're getting is we're getting very good local approximations, as in the Taylor series ends up trying to match derivatives of the function up to some particular order locally around this point. It is not trying to match the behavior of the function kind of globally over the entire interval. So the Taylor series expansion is very good locally, but it's not as great globally. And sometimes that's okay. But let's take an example of how we could use this in order to build the inverse function. So the inverse function, let's say we wanted to do A inverse, right? Well, we could end up writing A inverse in the following kind of silly way. Identity plus A minus identity. Okay, inverse. So why did I do it like this? Well, one of the reasons is that A inverse is singular. And so if we wanted to be able to expand this guy out in some kind of a series, then we basically will end up running invariably into problems expanding about 0. So what I've done is I've changed it. So now we're kind of expanding it about the identity. So if we're looking at a matrix which is very close to the identity, then this Taylor series expansion will actually end up giving us something reasonable. And so this series, if we do a standard Taylor series expansion for it, actually can be written as 1 minus a minus 1 plus a minus identity squared minus a minus identity cubed. And this will absolutely converge if the norm of a minus identity is strictly less than 1. Note, actually, this is kind of interesting in a way because of the fact that if a were negative definite and large, it also ends up actually guaranteeing divergence. So the absolute value of this guy actually tends to be really important, even if A inverse is quite small, and you'd imagine that it would be easy to approximate. This Taylor series analysis will break down, on both sides of the line. So in any case, that's the assumptions that we end up getting with it. And it turns out, because of this relatively slow convergence, we're going to want to try a different type of polynomial. Another type of polynomial that we can end up using are known as Chebyshev polynomials. And Chebyshev polynomials are a little bit different. Chebyshev polynomials, these polynomials try to globally approximate the function. And just to give you an idea about what the Chebyshev polynomials are, Chebyshev polynomials are actually an orthogonal polynomial basis. So we can, just like we use the poly operators to be able to represent any matrix, Chebyshev polynomials can be used in order to be able to approximate any function, just by projecting that function onto this basis of orthogonal functions or orthogonal polynomials. And the way that the Chebyshev polynomials are defined is T naught of x is equal to 1. T1 of x is equal to x. And then from that, we actually end up having, let me just make sure that I'm sticking with consistent notation here for the Chebyshev polynomials. Yes. Tp plus 1 is equal to 2x Tp of x minus Tp minus 1 of x. And so this in particular ends up meaning that T2 is equal to 2x squared minus 1. So on and so forth. There's a couple of really beautiful properties about Chebyshev polynomials. First is, they approximate I guess the first one I mentioned is that they form an orthonormal basis. So in particular, it's possible to end up defining an inner product between the Chebyshev polynomials, which is expressed as an integral over a domain, which is -1 to 1. And then this inner product ends up satisfying equals delta PQ. All right, awesome. So then there's an orthonormal basis that we end up getting for the operators. And the second is that the Chebyshev polynomial expansion that you end up getting for a function. So let sum over j, aj, t j of x be the Chebyshev series for f found by representing it in this orthonormal basis, then what ends up happening from this is we do this from t equals 0 to k, g equals, then g closely approximates the polynomial of degree k that minimizes the maximum deviation from the function f of x on the interval in question, which is we always assume is going to be rescaled for these polynomials to be between -1 and 1. Okay, so those are two of the really important things about it. The other thing, one of the other things that I should mention that's really kind of neat about Chebyshev polynomials is that they actually give you a construction that allows you to translate between trigonometric polynomials and ordinary polynomials. And actually, from this, you can actually derive a ton of trigonometric identities as one-liners using the properties of Chebyshev polynomials. So they're very powerful to use. And this is one of the reasons why they end up getting widely used everywhere from theoretical computer science on to actually mathematical physics and beyond. So these are going to ultimately be the functions that we're going to use for our purposes, but other possibilities end up existing. Another one that can be of value is Lagrange polynomials, and the basic idea here is that if we have some sort of a data set and we want to be able to find a degree, say 3 polynomial that ends up going through all of these points, the Lagrange interpolatory polynomial is the polynomial that of degree k that ends up going through k+1 points, that such that at each of these interpolation points, the error is precisely 0. Okay, so these can be valuable if we only care about approximating the values of a function that are stored in a lookup table at a discrete number of points. However, in most cases, because of all the theoretical nice properties that go with Chebyshev polynomials, most of the discussion in the literature ends up taking this approach over here. All right, cool. So now, by going through the orthogonality relationships for Chebyshev polynomials, it's actually possible to derive something very particular here. So here's a theorem. This was proven by Cathari, Childs, Soma, I believe. Dominic Berry might have been on this. I don't remember, but this was, I believe 2016. And the theorem is, this is for approximating x inverse. Okay, so let g of x equal for sum from j equals 0 to j naught, -1 to the j, sum from I equals j plus 1 to b, binomial coefficient of 2b, b plus I, divided by 2 to the 2b, t2j plus 1 of x. And let D, a domain of interest, be -1 through -x min union x min through 1. So what we've done here is we've taken our interval, which is the interval, that normally the orthogonality relationship for Chebyshev polynomials ends up holding for. And what we've done is we've just taken the x-axis between -1 and 1, and we have split off, kind of created this insulation layer between 0 and the rest of the spectrum, or not spectrum, the rest of the line. So we've cut away this open interval surrounding 0 of radius x min. Okay, and this of course is -x min and x min. So after cutting this away, we're left with this remaining region and two regions, and the union of those two regions we've called D. And the reason why we cut away this central region is the exact same reason why we forbade the operator to be too close to 0 up here. It's because if we end up having those kinds of divergences, then the degree of the polynomial that we need in order to be able to closely approximate the function ends up diverging. And if we literally include 0, then we can't prove any error bound, because if the user were to put in 0, then the error would basically be infinite for any finite degree polynomial that we end up picking. Okay, so that's the setup for some of the variables. Now, if we have this, then because we've padded ourselves away from this, we can have that the absolute value of this minus the true inverse on this interval is less than or equal to 2 epsilon if J naught is less than or equal to square root b log 4b over epsilon, and b equals x min minus 2 log of 1 over x min epsilon squared. All right, cool. So just to give an idea about how this is working, right? So if we plot our function, this is what x inverse ends up looking like, right? And we've cut it off at 2 distinct values over here. And we're picking this odd degree Chebyshev polynomial in order to be able to approximate it. And this odd degree Chebyshev polynomial will end up looking like this. Okay, so it's guaranteed that the deviation between the true behavior inside the region D, which again is the union of the two outer regions, is at most 2 epsilon in these two regions. But there's no promises whatsoever about what the error is in the intermediate region. So because of that, what we're going to want to do is we're going to want to make promises ultimately about the eigenvalues of the operator. So why the eigenvalues of A? Well, here's why. Let's talk more generally. What do we mean when we think about A inverse of a matrix? Okay, well, A inverse, if A is a normal matrix, meaning it can be diagonalized, then A inverse is equal to the inverse of U, D, U dagger, where D, this is the diagonal matrix of the eigenvalues of the operator. Okay, so this is just the matrix with the diagonal elements containing the eigenvalues of the operator, and U and U dagger are the two matrices that transform kind of like the row and the column basis of the matrix to the eigenbasis. Okay, so that is the inverse operation. Oh, and this is inverse of that. Cool. All right. So then let's just figure out if A inverse itself is diagonalizable, then we really need to be able to figure out a matrix that that will do this. U here is unitary, because just by definition of what we mean by an eigendecomposition, the transformation that goes to and from the eigenbasis is actually a unitary matrix in general. So that's unitary, because the inverse is the yeah, because the inverse of a unitary is its transpose, we can end up seeing that U d U dagger times U d inverse U dagger is equal to identity. Therefore, this has to be equal to A inverse. Okay, and D inverse, the inverse of a diagonal matrix, has to be, in order to get this times that equal to the identity matrix, this has to just be lambda 1 inverse all the way down to lambda 2n minus 1 inverse and 0 on the off diagonal. Okay, so basically, what am I kind of getting at here is that the inverse is actually, you can envision as being the inverse of the function applied to the eigenvalues. And so similarly, if we have a polynomial function over here, like let's imagine that we have g of a. Okay, and g of a we've defined to be is sum over j, a sub j, tj of x. Then this function over here, if we've chosen it in such a way so that the polynomial transformation that we end up getting will actually approximate A inverse, then we know that actually let's say tj of A over here, where tj of A, what I mean is just imagine expanding the polynomial. Like, for example, let's consider T2. Okay, I know T2 doesn't show up in the above expansion, but we've already worked out what T2 is. So T2 of x is equal to 2x squared minus 1. So therefore, T2 of A over alpha, if I'm worried about the normalization, which I will be in a sec, then this is A squared over alpha squared minus 1. Okay, so this is the operation, and when we go through and expand it in the its eigenbasis, we can end up seeing that T2 of A over alpha is equal to U to D over alpha squared minus identity U dagger. Okay, so that is T2 of alpha. Okay, and now this over here, if we apply this property to it, we actually will end up getting something that will be of the form U G of lambda inverse going down to G of lambda 2 to the n minus 1. Oh, shouldn't be inverse here. 0 here, there. And this is approximately equal to A inverse by our above discussion. So basically what I was trying to show here is that we know how polynomial transformations end up working. The polynomial of a constant that ends up making the inverse. If we apply this to a matrix, then this will all work, assuming that all assumptions about validity of G hold for all lambda I. Okay, so under those assumptions that all of our previous assumptions end up holding, then this is true. The thing that we end up requiring is that lambda I is in the set D, which again was this -1, -x min union x min 1. So if for all I. Okay, so what this ends up saying is that if we assume that not just the scalar ends up agreeing with the conditions that Cathari et al. End up laying out in their approximation, then what we end up having is that the polynomial approximation that we have to the inverse of a scalar function actually will end up applying to a polynomial, i.e. the inverse of a matrix. So that's the basic idea behind it. Now, what I'm going to do is let's just copy and paste. Interesting. I wonder if the quarter of my picture is going to show up. It probably will. That is funny. Okay, awesome. So this is the equation that we ended up having. Here, if you recall, J naught is the kind of degree of the polynomial that we want to build. So we really want to figure out what the degree of this polynomial is ultimately going to scale like. So if the value of substituting in B, we end up getting that J naught is in O tilde x min inverse log 1 over x min epsilon. And basically what O tilde means, in case you haven't seen it before, a function f of x is in O tilde g of x if, now it depends on the context, but if for some const a greater than or equal to 0, we have that lim x goes to infinity, g of x times log of x to the a over f of x is less than infinity. Okay, so essentially what this notation ends up meaning is it basically says that f of x is in order g of x, dropping all annoying log factors. Okay, so it's an even more qualitative version of the scaling than big O notation ends up doing, but this will drop any logarithmic factors or any doubly logarithmic factors, etc., that are not considered to be the dominant scaling. Now, there's a little bit of a trick here because it depends on what you consider to be logarithmic and what you consider to be linear when you're dropping it. So by convention, normally we define annoying to be non-leading order. So that's why I left the log 1 over x min epsilon in this expression, but I truncated all of the logs that we end up getting from the log for b over epsilon. Okay, so this ends up giving us the scaling of the polynomial. Now, from our this j naught over here, this is the value of k that we need to pick for our quantum singular value transformation over here that we using this circuit. And so in general, if you recall, this circuit that ended up block encoding, what it block encoded, sorry, I made a mistake here. This block encodes 1 over a for some scaling constant a. And that scaling constant here is going to be equal to the sum over j, a sub j, absolute value, is equal to a. Okay, so this value of a, it has a big impact on what the function is, what the block encoding ultimately ends up yielding. And in particular, another way of writing this block encoding notation is that if we pick out the block and assume this block is flagged by 0, tensor I for success, then we have another way of writing it is that if this circuit is, let's call it LF, we have that this projector onto this top block over here times LF multiplied by the projector on the input over here. This whole thing was equal to 1 over a f of a over alpha. Okay. Cool. And so the key thing about this is this ends up actually implying something about the probability of success, as you recall. So if we go through and we figure out, okay, well, what is LF acting on 0 psi times the projector onto identity multiplied through by 0 psi LF dagger. Okay, well, when we go through the math, we end up finding that this is actually equal to, this is the success probability. The success probability is equal to 1 over a squared times the inner product of psi f of a over alpha dagger f of a over alpha psi. Okay, and so now in general, what we end up having is we end up having that. Okay, not in general. In general, this is hard to figure out because of the fact that the success probability depends on the input state. So for some states, it's going to have much higher success probability than with others. So what we need to do is we need to be able to provide a bound that will be able to hold kind of more generically for this. Okay, this bound we can actually get by, well, let's just, whoops, that was kind of weird. Okay, so never mind. This bound that we end up getting on the success probability is, if you recall, now we're using G down here in order to be able to describe our approximation to F inverse. The probability of success here is equal to the expectation value now of G of dagger of A divided by alpha G A over alpha psi over A squared. Now, let's assume that G of A over alpha is equal to A over alpha inverse plus some small error of the order of epsilon from the theorem above by Cathari. Okay, so now furthermore, A, if we take a look at it, A is the sum over J, alpha sub J, Uj. Okay, and so therefore, the norm of A over alpha is less than or equal to 1 to begin with. And okay, that's cool. And so then what this ends up implying is because the norm of A over alpha is 1, then we end up having the norm of A over alpha inverse has to be greater than or equal to 1. Okay, because essentially the norm, if you recall, is the largest eigenvalue of a matrix. And the largest eigenvalue, the inverse of A over alpha, has to be at least the inverse of the largest eigenvalue, which is 1. Therefore, because of this, we can say that the probability of success is less than or equal to 1 plus order epsilon over alpha squared, which is in omega, which means lower bounded, 1 over A squared. Okay, fantastic. So this gives us a lower bound on the success probability in our context, which is just 1 over A squared. So now what we need to do is we need to go through this series over here and find A. So A here, let's just copy the definition. Hopefully it'll work this time. Okay, so when we take a look at the appropriate sum, what we end up finding is we end up finding that the coefficients of each of the t sub j's, each of these, if you take a look at the recurrence relation, we end up having t 2j plus 1 is equal to 2x tj minus, 2j, 2j minus 1. All right, so that ends up giving us the expression. So this ends up suggesting that the coefficients that we end up getting in the expansion of this can be rewritten as something that end up scaling like j equals 0 to j naught. Worst case scenario, this is going to go like 2 to the j divided by, or sorry, multiplied by sum over I equals j plus 1 to b over b plus I divided by 2 to b. Okay, this is an ordinary binomial sum. And so by taking a look at the limits of the appropriate binomial sum, it's actually really easy to end up seeing that this is less than or equal to 4, sum from j equals 0 to our maximum term, j naught of 1. The reason why is that the sum over I equals 0 to to the b, or sorry, of b to, or sorry, I guess yeah, all right, never mind. It's a straightforward example of binomial sum that you can carry out, and then bounding that internal term above by 1. This just ends up giving us that this is equal to 4j naught. Okay, so now we have that this is a bound on the coefficients that we end up getting. So this is actually just equal to the absolute value of a here. So we bounded the coefficient sum that we have for our particular expansion. So therefore, our probability of success ends up scaling like 1 over j naught. J naught is in order, or is in omega. Or sorry, no. We're going to choose j naught to be proportional to x min inverse log of 1 over x min epsilon, where epsilon is our error tolerance that we ended up having. And again, this is just using this guy here. Okay, so using that, I guess actually technically I mean tildes, because there's possible logarithmic factors that we've dropped. Okay, so given that, then what we end up with is that the probability of success here is 1 over j naught squared. And so if we apply amplitude amplification, then the number of repetitions needed to get success scales like a 1 over the probability of success. Square root, because amplitude amplification gets a quadratic speed up for exactly these types of problems. And so therefore, just by plugging this this all in, oh, did I get? Yeah, cool. All right. And so then the number of times then that we end up needing for this ends up going like x min log 1. Okay, great. So that is the let me just see what this is, because there's something funky going on here. Probability of success. Root the probability of success. The probability of success should end up going like no, okay, sorry, I made a reciprocal error here. This ends up just going like x min inverse log 1 over x min epsilon and no tilde. Okay, wonderful. So then that is the number of repetitions that we would end up needing of our fundamental algorithm in order to be able to get this to work. And so this is the number of times the oracle LF or the subroutine LF needs to be called. Now let's go back and look at what LF ends up looking like. So if we jump back, LF is this creature here, where we needed, again, J0 different polynomials. So the number of different registers that we have here is the degree of the polynomial, which was J0 here. And for every one of these bits, we had to select. And every one of these registers, we've got a different prep. So the total number of queries that we end up needing here would be, well, J0 preps here, J0 preps here, J0 selects here, and 2 prep as. So the total number of Oracle queries that we would end up needing for one of these operations would be 3 J0 plus 2, okay, which is in order J0. So going down to the final expression over here, we end up getting that the total number of times, or total number of queries, is in O tilde J0 over X min log 1 over X min epsilon, which again is the exact same thing that we had here already, which is just O tilde 1 over X min squared log squared 1 over X min epsilon. Okay, cool. And so now the key thing is that what we've implemented here is we've implemented A over alpha. And so if we want to be able to interpret this as the inverse of A, then we can think X min. This now becomes the same thing as lambda min of A divided by alpha, right? Just by translating this over here. And so then once we've rewritten our expression in that form, this ends up becoming O tilde of alpha squared over the minimum eigenvalue of A squared times these log factors over here. Now the X min, it technically disappears in the O tilde notation. So I'll just write this as log squared 1 over epsilon. All right. So this gives us the basic scaling that we need in order to be able to solve our problem. And that problem, basically, if you recall, it's been a while, but the problem was to take a ket vector B and map this to A inverse B. And we did this with a degree J0 or 2J0 technically polynomial, and using a total number of queries that ended up scaling like this. So if the queries can be done in poly and time, then this gives an exponential speed up relative to classical. And furthermore, I'd recommend taking a look at the original paper, looking at this. It uses a very different approach to solving the quantum linear systems algorithm. It goes through Hamiltonian simulation as an intermediate idea. But they end up showing that if a classical computer could replicate this in poly and time, then classical computing is polynomially equivalent to quantum computing. Okay, and so that is something which nobody believes to be true, and gives a very good reason to believe that this speed up is really unlikely in general to be one that classical computers can get around. So it seems like at first glance, this is an amazing algorithm. This provides an exponential speed up for a ton of really relevant problems, because let's face it, like almost everything, almost all problems that touch on applied linear algebra actually boil down to some variant of solving an inverse problem. And this gives an exponential speed up for it. There, however, has been actually a lot of challenges that people have run into trying to leverage this exponential speed up for real applications. And the problems that end up showing up are, one, B is generally exponentially hard to prepare. Two, if we want to know X and not just the expectation values of some operators in a state X, learning X is exponentially hard to do. Or three, the matrix A may not be conveniently decomposed into sum of unitaries. Now, this doesn't always, in principle, as we mentioned before, every matrix can always be written as a sum of unitaries. However, it doesn't necessarily end up implying that its decomposition in a poly basis is efficient. However, the subsequent work is showing that this can always be done if A is sparse and computable. And specifically, I mean row computable efficiently, meaning that we can find the locations of the non-zero matrix elements and their values in polynomial time in every row and column, and that there's only polynomially many non-zero elements. So it still is a relatively broad class, but it's that the third caveat I did want to mention. It's not as serious as the first two, but these three put together have meant that it's actually quite difficult for us to be able to come up with direct applications of the quantum linear systems algorithm. I would say that probably the most promising approach for this is solving differential equations with this, where basically the whole idea is, in that particular context, you take A to be a approximation to the derivative operator, or the Jacobian. And then what we do is we invert to find the solution. Okay, and so that is basically the key idea behind the differential equation solving methods. And if you're interested, I'd recommend taking a look at it. The original work by Barry, is done by Barry in about, I think, 2013, but there's been a series of improvements since then to these algorithms. And yeah, I'd recommend taking a look at work that Andrew Childs and his collaborators have done in this direction too. Okay, well, thank you very much. Hope you've enjoyed the talk. And next time, we're going to take a look at how to use this as these same ideas to solve the Schrodinger equation.